In this lecture, we're going to introduce a concept of internal energy, and we're going to have to talk about that in the context of changes in energy and heat and work. So let's start with the first law of thermodynamics. So, thermochemistry is generally the study of energies that are given off by or they're actually absorbed by reactions. We think of reactions as either giving off energy or absorbing energy. And that's what thermochemistry is really looking at. So, thermodynamics is the study of energy, two ofs, sorry, and its interconversions. So this kind of falls under that category. We'll talk about thermodynamics more also in Chemistry 163. So the first law of thermodynamics is the law of conservation of energy. And it states that the total energy of the universe is constant. The universe word being key there. So you can never design a system that will continue to produce energy without inputting energy into that system. So that energy of the universe, that change in the energy of the universe equals zero, right? And so that means that the energy of any system and its surroundings has to equal zero when we look at its change. So energy can flow between a system and its surroundings, but we can never just completely create new energy. And this is a foundational piece of how we think about thermodynamics. And it's such a, I mean, it's a law. And so it leads to things like, let's talk about patent law, right? So the idea of being able to create energy in a cheap, easy, effective way is very, very seductive because we have such an energy crisis at all times in human history. And our ability to innovate and to like level up our technology really is hampered by how much energy we can put into it. And so actually, and this is from U.S. patent law, that a rejection of a patent application on the grounds for lack of utility includes more specific grounds of inoperativeness involving perpetual motion. So a rejection under 35 U.S. C 101 would be for a lack of utility, should not be based on grounds that the invention is frivolous, fraudulent, or against public policy. Basically, you can't get a patent for anything that appears to be a perpetual motion machine at all because they're not real. But perpetual motion machines are fun. So Google or YouTube search perpetual motion machines. So here, like, there's lots of perpetual motion machines that people like to produce. They're fake ones. Hopefully this video is coming through okay. And these are all really fun to see. None of them could ever get a patent, and none of them are actually perpetual motion machines because they will slowly stop over time due to friction and just loss of energy into the system. But they're so cool to look at. So I strongly recommend doing a quick search on like top 10 perpetual motion machines of and any year, and you'll get to see some really cool ones. And so these are just a few. I think this is the ones that were listed for 2018. And so it's a fun treat. But so the idea is you can't continually create energy, right? It's always actually being supplied from somewhere else outside of the system. And so if we accept that, then we're going to be able to take advantage of the fact that we'll be able to track the amount of energy that flows between system and surroundings without worrying about increasing overall energy or losing overall energy within the system and the surroundings put together. Now, before introducing internal energy, I want to take a quick moment to talk about what a state function is. So, it's any mathematical function whose result depends on the initial conditions and not the actual process used. And this is my best analogy that I have for it. A state function, like if we're looking at the distance between Seattle's main campus, South Seattle College's main campus, and the Georgetown campus, we can measure the distance between the two in a couple of ways. One, we can do it as the crow flies. Like if you could do a direct line from the main campus to the Georgetown campus, you would be able to develop a distance, and that would be representative of a state function. It's just the initial, like location A to B, and what is the most direct path there. And so that's our state function. Path-dependent function would be one that then depended on like a driving route between the main campus and Georgetown campus, in which case you would have to go down Delridge, you'd have to go over, you'd have to cross the bridge, and then you'd end up down on the Georgetown campus. And the distance is going to be greater. And it's not always whether it's greater or less, but the idea is that the path is an important part of that function. So we have state functions and path-dependent functions. And we're going to talk now about internal energy, which is a state function. That means it's going to only depend on our kind of initial and final. So internal energy is the sum of the kinetic and the potential energies of all of the particles that compose a system. And so if we're looking in the change in internal energy for that system, we're going to look at it at the beginning, the reactants, and then at the end, the products. And so we're not worried about how the chemical reaction proceeds. We're not worried about how long it takes or anything like that. All we care about is beginning and end, and where is the internal energy at the beginning and end, and how has it changed. So looking at internal energy, we think of this as all of the energy. So that's kinetic and potential energy for the system. And we can say that if our reactants are going to be less stable than our products, when we talked about potential energy before, that means that they're at a greater potential energy if they're not as stable. And so a greater potential energy will correspond to a greater internal energy for that system. Remember, when we're talking about a system, we're focusing in on the chemical reaction taking place, right? Or the coffee in my hand right now. It's warmer than my hands. So when we have something that's less stable and it undergoes a chemical reaction transformation into something more stable, then that potential energy will decrease, and our internal energy total is going to decrease as well for our products compared to our reactants. And so it appears then that the system has decreased in internal energy at the beginning to the end of the reaction. And that means it's going to then give off that energy, that excess energy, into its surroundings. So energy is going to flow from the chemical reaction into the surroundings around it. And we call these reactions exothermic. So exo meaning it's like energy is exiting is one way I've heard of remembering it. A campfire that you would sit around is very exothermic. That's the way I kind of remember it because it gives off heat. And so we see this net change in energy for our system, and that's going to lead to a change in the energy of our surroundings. It'll increase the internal energy of our surroundings as it absorbs that energy lost from the system. So let's look at the opposite. So let's say we have reactants that are stable. They're really stable. So we're looking down here at our carbon dioxide. And they undergo a chemical transformation to form products that are less stable. So that would be our carbon and our oxygen in this case. Then what's happening in our system is the internal energy is increasing as we go from reactants to products because the potential energy is increasing because they just aren't as stable a bond. And so in this case, if we're going to increase that internal energy, we have to get that energy from somewhere, right? We can't create it from nothing. And so energy is going to flow from the surroundings into the system to supply that energy. You could think of it as the system is stealing energy from the surroundings to allow this transformation to take place. You could say that it's consuming energy, and so it's taking it from its surroundings. But we call these reactions endothermic. Endothermic. So whenever reactants go from a more stable to a less stable arrangement as products, There will be a net change in energy for that system, so just the chemical reaction, where the internal energy increases. And then we need to supply that energy from the surroundings. So energy is absorbed by the system from the surroundings, or the surroundings release that energy to the system. It's another way to think of it. So let's look at an example. So we've got an overall reaction for the digestion of sugar shown down here. And if you look at it, it's a combustion reaction, right? That's what your body does. Your body is a combustion engine. And it takes sugar and it turns it into carbon dioxide and water. And it takes all the energy from that process and uses it to spend that energy on lecturing at you about thermochemistry or drinking this cup of chai tea. So, so we're going to draw an energy diagram for this reaction showing internal energy. So just based on your personal experiences eating sugar, predict the relative stability of our products versus our reactants and indicate which direction energy will flow, either into or away from the system, for our reaction between sugar and oxygen. Why don't you give the video a pause and try to write this out yourself, and I'll do it here in just a second. All right, hopefully you've given this a try. So let's identify things as our reactants and our products. So thinking about our reactants versus our products, we're going to need to decide which one is more stable and which one is less stable. And we're going to do that by using our intuition about what happens when we consume sugar and what does our body do with that, or any other nutrient, honestly. So our body is going to take this and break it down into carbon dioxide and water. And the process of taking in food like sugar and then processing it into carbon dioxide and water is to extract energy from it. So that's going to imply that our energy is going to flow from that sugar reaction being converted to carbon dioxide and water into the surroundings to be used for other things. So we're going to give off and release energy. And so that means if we're going to release energy, our reactants need to be more stable, or sorry, our reactants need to be less stable, and our products need to be more stable. So thinking about our energy diagram, we've got energy as our axis, internal energy. And we have our, something's going to be higher potential energy, higher internal energy, one will be a lower internal energy. If we're going from less stable to more stable, remember more stable is lower in potential energy and lower in internal energy. So I'm going to put my more stable compounds, my CO2 plus my H2O, as the lower energy level, and my reactants at the higher energy level. Because as this transforms from my reactants to my products, I'm going to decrease the amount of internal energy that I have in my system, and that's going to release energy into the surroundings. And that's going to make this an exothermic reaction. So this delta E right here is our internal energy for our system. And so thinking about internal energy in general, that is that or the change in the internal energy of what we just talked about. It's that heat is flowing out in an exothermic or in as an endothermic. But it could be heat or it could be work that's occurring that represents the energy flow between system and surroundings. And so this can happen with heat and it can happen with work. And work, remember, is that force over distance. So that change in internal energy, that's our state function, right, is going to be equal to our heat plus work. So the total energy that flows between the system and the surroundings will be heat and work together. And so heat is represented as Q and work is represented as W. And these Q and W are not state functions. These are path dependent. And so our change in internal energy is the general flow of heat into or out of the system. However, our heat will be either the system gaining thermal energy or losing thermal energy. And our work will either be done on the system or it'll be done by the system. And this means that when it's always from the perspective of the system, the work being done on the system is the surroundings, let's say, pushing on the system if there's like gas evolving or being consumed. But if the system is doing the work, it'll push against the surroundings, is a way to think of it. And so we have signs for these like plus and minus, right, that we're going to attach to whether things are going in or out based on the system. And so defining the system versus the surroundings becomes key in understanding if something has a positive or negative symbol associated with it when you're trying to quantify heat or work or energy. And so for heat, from the perspective of the system, let's take my T, all right? And my hands are the surrounding, and the T is my system. So for heat, the T is hot and my hands are cold. And so the system, the T, will lose energy to my hands, the surroundings. And so the heat would, the amount of heat that travels or transfers from the T to my hands would have a negative symbol because it's being lost by the system, the T. Now, if instead I put this in my oven or my microwave and heated it up, then I would be taking heat from the surroundings of the oven and it would flow into the T and heat it up. And so then the system would be absorbing energy from the oven or microwave. And so it'd be gaining thermal energy, increasing temperature. And so it would have a positive symbol associated with the heat that flows between the oven and the T. So it's all relative to the system, which is the T. Now, if it's work that's occurring, work being done to the T, so pressing on the T, like maybe the pressure of a gas evolving, that would have a positive symbol. The work is being done to the T, so it would be positive. Now, if work is done by the T to the surroundings, like let's say it evaporates, turns into a gas and like pushes out against the atmosphere, then it would be the system doing the work. And we would say it would be losing that energy through work to the surroundings, and so it would have a negative symbol.